Hi there, everyone. All right, so at this point, you should be done your kinematics section, which is part 1 of physics, and preparing for your test on Monday. Now, I asked you to send me any questions you wanted me to go over. I only received a couple, so this will be a fairly short video, but then I will be posting the answer key after as well. So the first request I had was to go over actually an acceleration question, which was, number 4 of the acceleration section. So this is actually on page 19, number 4 here. All right, so we're dealing with acceleration. First what I like to do is when I read the question, I underline any important information in order to figure out kind of what formula to use. All right, a car is initially traveling at a velocity of 4.2 meters per second west. If the car's average acceleration is 0.86 meters per second squared west, how long will it take the car to reach a velocity of 9.6 meters per second west? Okay, so I'm going to start by just writing what I know. I know that my acceleration is 0.86 meters per second squared west. I'm solving for how long, which is going to be time, and I have two velocities. So in this case, I actually have a final and an initial velocity. So I write my initial as VI, and that would be my 4.2 meters per second west. And my final velocity, VF, is 9.6 meters per second west. So when we're solving for acceleration, we know that there's kind of two styles of formulas. There's just the regular A equals V over T, but really that velocity is kind of like the change in velocity. So it can also be written as VF minus VI over T, where this VF minus VI is that change in velocity. So that's going to be the formula we're going to need here because we have both velocities. All right, now I sub in the information that I know. So my acceleration was 0.86 meters per second squared west, and my two velocities, sorry, I'm running out of room there, and I'm dividing by time, and I keep that as t because it's an unknown variable. Now in this case, I would actually just do that math first, just to clean up the numbers a little bit. So I'm going to rework that as 9.6 subtract 4.2, and I will write that as my new velocity. So 0.86, I'm just dropping down that acceleration again. All I've done here is I've actually done that subtraction, and that equals 5.4 meters per second, and it's still going to be west. That way I just have one velocity to deal with. Okay, so how do I solve for time here? Time is on the bottom of the fraction, which means that actually the very first thing I have to do is bring it to the top of the equation. We can't solve for it on the bottom there. So to do that, I do the opposite operation, and I'm actually just working with that variable. And I do the same thing to both sides. So time on this side cancels. All right, and now I have t times 0.86 meters per second squared equals 5.4 meters per second west. My next step is still to isolate that t. So I am now doing the opposite operation and dividing out the 0.86. All right, and I do that to both sides. Divide by 0.86. These cancel here. So what I'm left with, sorry, I'm changing colors a lot here. T equals, so this has all canceled. I now have left 5.4 divided by 0.86, which leaves me as 6.27906, which we will round up to 6.28. Notice how we haven't been doing significant digits, so typically I often like to just leave 2 decimal places, but you're not really wrong if you do more than that, all right? But try and have at least 2 decimal places. Okay, so that was question 4. Now I'm going to move on to the review. So the back of the booklet here. So do make sure this is going to be everything on that test. It is going to cover more heavily on speed, velocity, and acceleration and graphs, but there will still be some scientific notation, metric conversions, and distance and displacement. All right, so make sure you're familiar with your formulas. Obviously, we have our distance and our displacement formulas, and then we have our velocity or our speed formula and the acceleration formulas. So make sure you're familiar with those and the units that everything comes in. All right, I'm going to start with actually just a conversion question. Number 2, and I'm on page 22. So throughout the unit, you're going to have to convert numbers, and this was kind of the first thing that we did. First, you start by writing your initial value as a fraction. Okay, so I just put it in that format. In order to convert to meters per second, I'm going to need 2 conversion factors because I need to convert 2 units. It doesn't matter if I'm dealing with time or distance first. Either of these could be swapped. I'm going to start with time. Okay, in order to cancel out hours and convert it to seconds, I need to have hours diagonal each other across the multiplication sign. So see how they're on the bottom and top. Okay, that leaves me with 3,600 seconds on the bottom. Remember, this here is called a conversion factor, which means the top and the bottom are equivalent to each other, but they're just representing different units. Okay, that leaves me with kilometers. Kilometers now has to go on the bottom in order for it to be able to cancel, and there are 1,000 meters in a kilometer. So now any unit that was diagonal from each other can cancel, but remember, I'm only canceling the units, not the actual numbers. So that leaves me to go 150 times 1 times 1,000 divided by 1 times 3,600 times 1. I multiply out the tops and I multiply out the bottoms. So 150 times 1,000, obviously that's 150,000 divided by 3,600 leaves me with 41.6, and I'm going to round off 67, and the units I had left was meters per second. All right, so that was just a quick refresher of those conversions. Okay, I'm going to move on. Sorry, I'll leave that up for a second. Next, I'm going to do a scientific notation question quickly. So I'm on question 3, and I will do 3A. All right, so we are converting these standard numbers into scientific notation. The first rule you need to know with scientific notation is that the decimal has to go after the first digit that is not a 0, okay? So it has to go after the first digit that is not a 0. That's just a rule. So the first digit that is not a 0 is 2, and the decimal has to go after it, okay? Then I'm always going to be multiplying by 10 to the power of something. And whatever that power is however many times I moved the decimal from where it was in my original number to where I had to put it, okay? Imaginary decimals, if there's nothing there, it's always after the very last digit. So that's where it was, and where I had to put it was here. So I had to move it 1, 2, 3 spots. That's where my power becomes 3. Okay, now there are also negative powers. So if I look at number B here, I have to put the decimal after the first digit that is not a 0, so those don't count. So the decimal has to go after that 7. It's always going to have the times 10 to the power of something. Okay, my original decimal is obviously here. I moved it 1, 2, 3 spots as well. But in this case, because my original number was less than 0, my power is negative. Okay, so if your original number is less than 1, your power is negative, and if your original number is greater than 1, your power is positive. All right, that's that. Okay, the next one I've been asked to do is number 5. All right, the velocity of a car increases from 2 meters per second at 1 second to 16 meters per second at 4.5 seconds. What is the car's acceleration? All right, so we're solving for acceleration. Now, we have a few different numbers here. I have 2 velocities and 2 times. My initial velocity is 2 meters per second. My final velocity is 16 meters per second. And I also have 2 times here, okay? Remember our formula here is kind of VF minus VI over T, or starts as kind of delta V over delta T. Those delta symbols mean change in. So in order to calculate my change in time, I just need the difference between those two numbers. So my change in time is going to just be the difference between those, which is 3.5 seconds. Okay, the car accelerated between those two velocities in 3.5 seconds, right? Because we don't have the information between 0 to 1 second. So then I just plug in my numbers. Final velocity minus initial velocity divided by my change in time, which is 3.5 seconds. And calculate that. Oh, it works out to an even 4. And make sure you remember your appropriate units, meters per second squared. All right. Okay, next one I'm going to jump to is number 10. So make sure you know some graphing questions. All right, back to kind of distance and displacement here. So Katie walks 8 streets towards the north to get to her friend's house. At the end of the evening, she walks 4 streets south, stops to tie her shoe, then walks another 4 streets south. What is her overall displacement? So in this case, I'm dealing with, I don't have positions. I'm calculating displacement. I could draw myself a picture, or I could do vector addition. In vector addition, north is viewed as positive and south is negative. All right, so 8 streets north, I would write as positive 8. And I'm adding to that 4 streets south, so I make that negative. Her stopping doesn't really do anything for her displacement, so we just leave that out. And she walks another 4 streets south. When I work that out, that works out to 0 streets. So that's an example of what vector addition would look like. Okay, you could have also drawn a picture, figured out the same thing. Okay, next I'm going to do number 11. It's slightly different here. Sam starts at a position described by -9. So here's the difference. I have a position, which is an actual place in regards to a reference. Okay, walks to a position of positive 25. So this is not saying walking 25 meters north. Okay, walks to a position of 25. So let me just show you on a picture what this would look like. If I'm given position, that means 0 is typically my reference. If I am starting, let's say at -9, this is where Sam starts, and the position of positive 25 is 25 steps or whatever from 0. So I'm trying to figure out the total displacement here. All right, what you can also do with position is use the formula df minus di, where it is final position subtract initial position. So my final position was that positive 25. I minus a -9, which ends up actually being positive 34. And according to my picture, I can see that Sam would have had to have walked positive 34 steps in order to get from -9 to positive 25. All right. I think that's all I'm going to do. Nobody else had any questions. Later this weekend, I will post the answer key as well. All right, good luck. Take